Alright, my name is Mayuri and I've been asked to give you a talk on some instrumentation techniques in radio astronomy. So I'm a radio astronomer. We will take it slow and we'll get as far as possible, and those who are interested in knowing more, I have a bunch of references. So I'll make the slides available and so on, so you can use those references to understand more. And just because when I started making the slides, I realized that I cannot cover both of them and do justice to both of them in an hour. So I'll focus mostly on radio astronomy, and if we get the time, we'll move on very short, small section on submillimeter astronomy. Again, slides will be available, you can take a look and we can chat later if you're interested, okay? Now, quickly, quick few questions. How many engineering students in the room? Okay, good, okay. And how many of you have had any sort of exposure to radio astronomy or, yeah, okay? Okay, that's pretty good, okay, great, okay. All right, so the reason why I asked is historically radio astronomy has been an engineering type of a field just because of the way it started. So I want both the engineers and the physicists in the room to relax, because you'll have a bit for everybody. Okay, so I will go slow, like I said. We'll cover these topics and we'll get as far as we can. Because generally when you think of radio astronomy, if you've had exposure, the one thing that many of you would have heard of is something called interferometer or interferometry. That comes a little later in our slides, but we'll build our foundations first. And things I will not cover at all are things like spectroscopy in radio astronomy and polarimetry, but you should understand that if essentially, like all of astronomy, even in radio astronomy, what you're doing is sensing electromagnetic waves or some photons from astronomical sources. And just because it's an electric field, it has properties that it has polarization, it has intensity, and it has some dependence on frequency. Okay, so the dependence on frequency, or trying to split a signal you get into multiple frequencies and studying that to understand something about the source, is spectroscopy. And polarimetry, as the name suggests, is you do something to understand the polarization of the source, okay? But we will not touch those things today. I've taken pictures from all over. So there are some standard astronomy textbooks, radio astronomy references that I've used. So I'm not explicitly going to give credit wherever, but that's what it is. Okay, so I think this is the specific kind of wavelength type of talk I think you're listening to. So far you've covered fundamentals of astronomy, GR, radiative processes, which is very relevant, and our starting point for this talk after this is radiative processes. But the sky is bright at different wavelengths because different objects emit different wavelengths, or their spectra peak at different wavelengths. You and I, we can see invisible. Our sun peaks in visible, right? But there are other objects in the sky, in the universe, that emit very bright at radio frequencies, okay? I'm sure all of you have an intuition of what is radio and radio frequency. We'll come to that in a bit. But for example, the kinds of things, am I blocking your, okay, I need to be here, I'll get off the stage. Okay, so the most abundant element in the universe is hydrogen, okay, and neutral hydrogen is bright in radio, okay. So you know that a neutral hydrogen atom is very simple. It has a proton and an electron. The spin of the proton and electron can be either aligned or anti-aligned, okay. It's typically a forbidden transition, it takes forever, but occasionally the spin of the hydrogen atom will flip from being aligned to anti-aligned, because this is a more favorable lower energy state. This spin flip emits a photon. This photon has a rest frequency of about 1420 megahertz, which is a radio frequency, okay. And just because there is so much hydrogen in the universe, it's a very abundant element. The universe is bright in radio frequencies and hydrogen, basically where there is gas, neutral gas, okay. For example, our galaxy has neutral hydrogen, so you can make a map of our galaxy at 1420 megahertz and it will look something like that, okay. That's not a very great picture, but you can look up radio maps of our galaxy at 1420 megahertz. Other things, they're very bright energetic phenomena called active galactic nuclei, or AGNs. Essentially, these are also called colloquially radio galaxies. These are distant galaxies and they have supermassive black holes that emit very bright jets that go off deep into space. and they are also bright in radio. Some of the very fastest transient phenomena, okay, things that have been relatively recently discovered called fast radio bursts, FRBs, are again something we study in radio. There are radio pulsars, which again, as the name suggests, you can observe them in radio and they emit periodic pulses, and these can be used like more or less like precision clocks because they are that periodic. These are neutron stars that are spinning and that have emission from their poles, and as it sweeps across your line of sight like a lighthouse, you see pulses, okay. There are also some, and this is the kind of stuff specifically in our group here at RRI we are studying. I think there may be some projects on offer as well. We study very faint cosmological signals also in radio. For example, the 21 centimeter I told you is local, right? It's a 21 centimeter in the rest wavelength or 1420 megahertz in the rest frame frequency. But the same thing if you try to study hydrogen from the early universe, there is a concept of cosmological redshift. Like the name suggests, you take the wavelength and you stretch it out, it goes to a longer wavelength or a lower frequency. So you can study neutral hydrogen at much lower frequencies and hence study the early universe and hydrogen from the early universe, okay. But because it is from the early universe, it's also very faint. There are other things that come in the way, and these are details I won't go into today, but you can study cosmological signals at radio frequencies. And the other thing that our own galaxy is bright in, did you cover synchrotron radiation yesterday, kind of, sort of, or? Okay, don't worry about it. So basically there are electrons in our galaxy, okay, these are called cosmic rays, cosmic ray electrons, and our galaxy has magnetic fields. So you know that when there is acceleration of a charged particle along magnetic field lines, it emits electromagnetic radiation, right? And this is abundant in our galaxy, and this because the acceleration is at relativistic speeds, it emits something called a synchrotron radiation, okay. And again, our galaxy at low frequencies, about 100 megahertz or so, is very, very bright because of the synchrotron radiation. So we can study structures and magnetic field lines in our galaxy at radio frequencies, and use that to understand galactic structure. So this is just a flavor of things we study in radio astronomy, okay. Very quickly I'll touch upon submillimeter astronomy. The boundary between radio and submillimeter is kind of blurry, but I'll touch upon what starts making the distinction. But radio frequencies are technically lower in frequency, say up to something like 10 gigahertz or so, and above that up to almost like a terahertz, okay, or hundreds of gigahertz. We call that submillimeter and millimeter astronomy. And in that there are other objects that are bright by the same logic. Our universe is filled with light that comes to us from the very early universe, very close to what is popularly called as the Big Bang, okay. So the radiation that gets released from the Big Bang after about 100 or few 100,000 years after this Big Bang comes to us today, and by the same concept of redshift, today it is visible to us at around 150 gigahertz, okay, and that light we call as the cosmic microwave background radiation. This is an image of a map of the cosmic microwave background. There are other phenomena we can study. For example, you might have heard of this thing called Event Horizon Telescope that made a map, the very first image of a black hole, including our own galactic black hole, and that was done at these submillimeter frequencies, okay. And we can study things like look into the birthplace of the a planet, okay. So that's something called as a protoplanetary disk. You can see that there is some object and it's sweeping rings and accumulating debris, and that's forming a planet. So we can look deep into planet formation, right. So this is something that we can do at very high frequencies in radio astronomy language. For optical and X-ray guys, this is low frequency, so we won't mix it up, okay. So again, we don't talk necessarily in terms of wavelength in radio astronomy, even though they're interchangeable, C by nu is lambda and so on, but we talk more in frequency, okay. Optical astronomy is probably the oldest field of astronomy because that's what we can see. So people could observe stars and sun and planets and their movements, and that's a very, very mature field. But very close to that, relatively compared to the other fields of astronomy, radio astronomy is very mature, okay. And the origin started closer to the World War, but more the discovery that there was something called as radio waves coming to us from astronomical objects was discovered kind of accidentally in the 1930s. okay, and that's an example of an old radio telescope, okay. And you might have heard of, this story of pulsars being discovered by Jocelyn Bell Burnell. So it's a relatively mature science compared to newer fields like X-ray, gamma ray, and so on, okay. And the reason for that is because, as you might guess, you can do radio astronomy from Earth, okay. Everything else, all the other fields in other than optical and radio, you have to go to very, very high altitude, if not outer space, okay. And this is, that image just captures that. Just a second. Yeah, yes. This is not planetary atmosphere, this is protoplanetary disk, which is to study the formation of, because radio waves are not really extinguished by dust, okay. So you can peer deeper into a dusty medium, but you do study planetary atmospheres at very low frequencies in radio, which I have not touched upon here, but you need to be in outer space for that, okay, because that's at very, just like you have aurorae on Earth, right, our sun's interaction with our magnetic fields lights up our atmosphere, ionosphere. Similarly, we expect other planets to have aurorae, which are very, very low frequency at which they are visible in radio. So people are exploring that, but they are so low that you have to go to space. Okay, this doesn't work, is it? Okay. Okay, sure. Okay, great. Okay, so right. So X-ray, gamma ray, you need to go to outer space. Visible comes to us, radio waves come to us as well, and to some extent submillimeter waves come to us. Because we may not touch on submillimeter astronomy for time, I'll quickly tell you that to do submillimeter astronomy, one of the problems is our own Earth's atmosphere, okay. There are things like water vapor, ozone, right, these molecules, and these molecules can absorb emission coming from outer space at submillimeter wavelengths, because they kind of correspond to the rotational and vibrational energy levels of these molecules. So they resonate at those frequencies, right. So you have to go to very high altitudes, sites like Ladakh, Atacama Plateau, right. The South Pole is very high, even though you may not have thought about it, South Pole is really tall. So you have to go to high and dry sites with less precipitation, very little water vapor in the atmospheric column to do submillimeter astronomy from Earth. Else you go to space, but it's more complex and expensive. Okay, all of these are radio telescopes. Most of them look nothing like the other, okay. The most familiar type of radio telescope you might have seen is something that looks like that, which is basically a parabolic dish. A small dish antenna, TV antenna on your terrace looks like a smaller version of this, okay. The larger the size of this dish, the higher its collecting area, just like the name suggests, it's a bucket that collects light. So more light it collects, the more sensitive it can be, okay. We'll also come to the other concept, but the larger the dish, the smaller the objects it can see, okay. The resolution is finer if you have a larger dish, okay. So this, does anyone know which radio telescope this is? Yeah, okay, good, okay. What about this? I'll give you a clue, this is also in India. Yeah, it's a Ooty radio telescope, okay. We don't have time, but you should look up what's special about this radio telescope. It's a very special telescope. Yeah, so corresponding to the latitude, that's the angle of the slope on which it sits, which means it has to do less work to track the rotation of the Earth, okay. This is Green Bank, this is Arecibo, which is no longer working, but there's a even bigger telescope called FAST in China. This is not a steerable parabola like this. It's a hole in the ground which has been used to make a radio telescope, and the receiver is on the top. So whatever rays come from all directions go to the focus here, and you can move this feed around. So the current biggest of this kind is fixed on Earth is in China, it's called FAST. This is the Murchison Wide Field Array, MWA. Again, there are no dishes here, right? You don't need a dish to make a radio telescope, okay? What you need is an antenna, and a parabolic dish is a type of an antenna, okay? And this is something that we are building in the lab here, which is something hopefully will go to space and orbit the moon and try to study the early universe. So they can come in all shapes and sizes. I already touched upon this, but like you can give me a little bit more rational explanation why. Broadly the frequency range is 0 hertz, because why not, to something like 1 terahertz, and then you start going into other frequency ranges. All these definitions of frequency range in astronomy are blurry, okay, they are not very well defined, but let's say this is the range for the total radio astronomy band we are talking about. From, oh, read this wrong, this is 2 kilohertz, my bad. From Earth, the 10 megahertz, you can't go lower than 10 megahertz. Can you guess why? Not quite, good guess. That's another problem. Which layer of the atmosphere? Ionosphere, yeah. So the ionosphere is basically plasma. It has protons, electrons floating around. Electrons are lighter, they move faster, right? So they have something called group velocity. So they can dissipate the radio waves that come in from outside and vice versa from inside, okay? And this has something, based on the number density of the electrons, we again focus primarily on electrons, but protons are also a factor. Based on the number density of the electrons and based on, of course, mass of the electron and the frequency that you are discussing, there is something called as a plasma frequency, which is like a cutoff frequency beyond which you will not be able to propagate the radio waves. It becomes optically thick. You have heard of this concept hopefully yesterday and day before, right? And what about in space? If I tell you that I go to like outer space, I go outside our ionosphere, I still tell you there is a 2 kilohertz cutoff. What's the problem there? Why can't I go below 2 kilohertz? The logic is the same, by the way. The reason why this happens is the same. Yeah. Whose atmosphere? No, not quite. I kind of misguided you. Our space is not really perfectly empty, okay? I mean, there are, of course, it's mostly vacuum, but there are electrons and protons, kind of free electrons and protons in the, what we call the interstellar medium. As the name sounds, it is between stars, and that has its own plasma frequency, but it's very, very low because the density is very, very low, okay? So there's a formula, straightforward formula that I can leave it as an exercise. It's in all the references I'll give you. You can work out for yourself how to get this cutoff number, okay? And then you will realize that this plasma frequency clearly is not a strict number. This 10 megahertz can be 20, 30 megahertz on a very active day when the sun is very active during the daytime, because there is more disintegration of the ions or molecules in the ionosphere. Okay, so the next distinction we'll come to between different techniques in radio astronomy is broadly called coherent and direct. I won't call it incoherent, but it's basically the same thing. So coherent detection system is any system in which you can preserve the phase of the signal you're trying to measure, okay? Broadly, that falls under the category that you're trying to, what you're sensing is a wave or a field, okay? Direct detection systems, you don't retain the phase, okay? Which means it's also something like you can treat the detection system as a particle detection system. It's not always true, but that's a good rule of thumb, okay? Which means it's hard to think of a phase for a particle, okay? You detect a particle, okay, and you just detect it, right? But for radio wave, you can think of it as a concept of a phase, okay? So which also means typically at lowish frequencies, you can employ coherent detection. At very, very high frequencies, 1 terahertz or so, you go to direct detection systems. You have different types of detectors, okay? You can also do coherent detection at high frequency, and maybe, I don't know how many of you have already covered this in your classes. There is a concept called heterodyning, which means you take a signal that comes at a certain frequency, you multiply it with a signal at another frequency, in our case a lower frequency, then the product that you get a product at low and high frequency, okay? So the lower frequency product is something that now you can do a coherent detection, okay, because the technology is available. So to do coherent detection of very high frequency, you necessarily have to do heterodyning, okay? But otherwise, broadly, coherent is phase is preserved, direct detection, no phase. Think of it just, yeah. Oh, let me try to get this, okay. So you have, okay. you have a signal coming at some frequency f1, okay. I have another signal that I generate, assume f1 is very large, okay, it's a very high frequency. I have another signal that I can generate that I call a local oscillator, okay, it's at a low frequency because I can generate it in my lab. Then you get a product, okay. The product from signal theory has, you get two products, okay. One is f1 plus, basically is f1 plus minus FLO, okay. So you get two products, okay. The f1 plus FLO is clearly even higher than f1, but f1 minus FLO is lower than f1. So by choosing an appropriate FLO, I can get a new f1 prime which is much lower than f1. Okay, so this is called heterodyning, okay, and I can now use direct detection because it's mostly technology limited, whether you can do direct detection or whether you can bring the phase information or not, okay, the type of technology you use changes, okay. So now I can use direct detection on this product. F1 is the initial signal you are getting from your telescope, or that is your original signal. Lower frequency, yeah. So LO stands for local oscillator, not low, but good way to remember. Okay. Okay. Here I am going to touch upon some things you have already covered. I hopefully won't have to go into too much detail, but the concept is that you have a radio source, it is emitting some power, okay. I can take a ray approximation along a thin line like a pencil beam, and the power in that pencil beam is related to this quantity that I defined called a specific intensity. Okay, so specific I nu is nothing but dP divided by these terms. Okay, cos theta is the angle, theta the angle it subtends, d omega is the actual angular area that it subtends, d sigma is the surface area of my detection, okay, on which this ray is incident, and d nu is the frequency, okay. So this I nu here denotes that it is a function of mu, okay. So it is specific intensity, okay. It's also sometimes interchangeably used as a term called brightness, okay. Now there's another term called flux, okay. Flux is nothing but I just integrate the specific intensity over the angle, over the object, okay. So there's an integral over d omega here, and flux is a standard unit in radio astronomy, okay. So if I take for a radio telescope or a source and it has subtends an angle some delta omega, my flux density there is I nu delta omega, okay. This is something that you have touched upon in radiative transfer, okay. The reason why I bring up this topic here is because in radio astronomy we operate in the Rayleigh-Jeans approximation of the black body spectrum, okay. So very quickly, this is the, I took out the equation of the black body spectrum, but 2 h nu cube by c square 1 over e raised to h nu by kt minus 1, okay, standard formula, okay. Now, so in radio astronomy, for all purposes, this is the limit in which we operate. H nu is much less than kt, okay. This has been, in fact, before the Planck's law was found, this was experimentally measured, okay, that's the Rayleigh-Jeans law, okay. And if you ask me, okay, how do you know at what h nu is it much less than kt? This is kind of a typical number. Again, let's say 10 gigahertz is that frequency. Below 10 gigahertz, I will say it is Rayleigh-Jean, about not so much, okay. The not so much I'll come to quickly. Right, and this is how you get that approximation. You do a Taylor expansion of this term, and because h nu is much later than kt, all the higher order terms disappear, and this denominator in the Planck's equation becomes this, and terms cancel, and you get this, okay. So the temperature, okay, you have an, this temperature T is called the brightness temperature, okay. It so happens that for most objects at radio frequencies, when you make a measurement, the brightness temperature is proportional to the thermodynamic temperature. Thermodynamic temperature is the actual temperature, physical temperature. You touch it, it's hot, cold, that is the thermodynamic temperature. Brightness temperature is not a real temperature, it is like an equivalent temperature, but in the Rayleigh-Jeans approximation for most radio objects, okay, most things that are black bodies that are in local thermodynamic equilibrium, brightness temperature and thermodynamic temperature are very similar or very proportional, okay. And that this brightness temperature is because we are talking about a black body. For a black body, specific intensity and brightness are the same. So hence I can replace my brightness by specific intensity, and in my radio telescope, if I am able to measure the flux, okay, I can get the brightness temperature of the object and maybe even deduce its thermodynamic temperature. Okay, anyone wants me to repeat that? Yeah. What is? Oh, okay. This limit is just telling you up to what point can I say that I can ignore the Planck constant. Okay, there is no Planck constant here, right? That means I can treat it as wave nature. I don't have to treat this as some quantum phenomena. Okay, I can treat it as wave nature of light, and hence I will go on in coherent detection aspects. Okay, but so this just gives you a rule of thumb number, some 20 gigahertz, much below 20 gigahertz or so, I can treat it as Rayleigh-Jeans approximation is valid, which means I can simplify. I don't have to write the black body equation every time to solve whatever I am measuring. I can just assume this is the relationship between brightness temperature and brightness, and in the optically thick limit, brightness is same as specific intensity. Okay.
So we are basically considering neglecting the quantum effect.
Yes, yes. So there is no H anymore. Okay. Yeah. Okay. So I'll quickly summarize. If I go out and make a measurement with a telescope, okay, assume it's some dish, and what I measure is some flux units. Okay. I can, from that flux and knowing the size of the object, okay, I can calculate its brightness temperature and hence its thermodynamic temperature. I can say something about the property of the object way out there by measuring how much power I am receiving in my telescope and what's the size of the object. Okay. How do you find the size of the object? We'll see. Okay. Okay. Now what? Yeah. Yes, yes, because in the limit that it is an optically thick object, okay. We will talk later about the equation, okay, but yeah. So in the optically thick limit, the intensity and the brightness are interchangeable, okay. Okay, very quickly, I won't be using this unit ever, but if you do any radio astronomy anywhere in the world, this is a unit you need to know. There's a unit called 1 Jansky. Because objects are that bright or dim, that's typically its order of magnitude 1 Jansky or 100 millijansky, right? That's a natural unit. It's about 10 days, it is 10 raised to minus 26 watts per meter square per hertz. Okay. So if I operate in watts, then I have to do 10 raised to minus 23, 26 calculations, which are weird. So you define the baseline unit as 1 Jansky. Okay. Okay. Now what happens in the limit when it's not quite Rayleigh-Jeans? Okay, the question one of you asked, right? So there, this is your approximation, okay? So this is in submillimeter frequencies, okay, typically like 100 gigahertz or so. There you define something called as radiation temperature, where h nu by kT is approximately equal to 1. So then this is the approximation of the Planck's law.
So that's how they detected CMB.
Yes, yes. So CMB was detected slightly differently. It was actually detected at much lower frequencies, not at its peak. It was done from Earth, but it was detected around like few gigahertz. But so they didn't have to worry about all this. But now this is the regime in which things operate in space or high latitudes, high altitudes. Okay, so now we come to the detection aspects of it. Okay, so this is a fundamental block diagram of a receiver. It has, this is a standard notation of an antenna, something like a V symbol. It connects to an amplifier, which as the name sounds, it's a radio device that amplifies the signal. It will also amplify the noise. Okay. So there are some special types of amplifiers called low noise amplifiers that are designed using special materials, where you amplify the signal more than you amplify the noise. You always amplify noise, but you add lesser noise, okay, compared to other standard amplifiers. Then say assume you have to do this down conversion, we've already talked about this heterodyning etc. You mix a local oscillator, the output frequency is called intermediate frequency or IF. Then you can amplify that IF, you can do one more down conversion if you want. Basically you bring the signal down to a frequency that your digital electronics or the rest of your receiver can handle, okay. And then this is called backend, where typically you will be hearing about this I guess on Friday from Girish, where he talks about digitizing, sampling, etc. Okay. So you have done this signal coming from the antenna, going through some electronics, amplifying, filtering, some multiplying, and then coming to a receiver. Yes.
Is that what you call a super heterodynamic if you do multiple times? Or is it different from?
No, it's the same thing, yeah. Okay. So the first aspect is what the antenna does itself, okay. An antenna is a sensor. It senses electromagnetic waves, fields, and converts them to a voltage, okay. The way an antenna operates is given here, I'll touch upon it, but one very important thing to remember, which is the whole thing premise of a lot of radio astronomy or any type of antenna operation, is that it is a reciprocal device. What you send in will come out, what you put in will come back. So they are, the way it behaves as a transmitter is the same as the way it behaves as a receiver, okay. So this is called reciprocity, okay. So let's treat in this case an antenna as a transmitter, okay. So this type of antenna is called a dipole antenna or half wave dipole, okay. It's a piece of wire, so you are assuming it's a perfect conductor, okay. It has a certain length and you are connecting it to some voltage source, okay. This is an RF voltage source, radio frequency, that means it's AC current, it's not a constant voltage. The voltage polarity changes, it's like a sine wave you are feeding it, okay. It goes positive, negative at a certain frequency. You are not moving this dipole, it's not a, yeah, so you are not, a dipole is not going to spin around, it's just a piece of metal when you connect a voltage to it, okay. What happens is, let's take this case first. The circles here is the magnetic field lines, okay. This is like thumb rule, right hand thumb rule. So initially you are applying negative voltage here and positive voltage here, that happens to be the polarity, okay. Just by virtue of potential difference, the top part is positive, this is negative, this is positive, this is negative. So current flows in that direction where the blue arrows are, okay. And this shows you the distribution of the electric field, the blue shaded region, okay. And the dashed lines are the magnetic field lines, right, straightforward, okay. Now, when you apply current here, there is current flow, charges accumulate at the ends, because where will it go, right? It cannot just jump out of the wire, okay. So there is an accumulation of charges and then your electric field will collapse, because your electric field is, your voltage source is changing polarity, okay. And then the magnetic field also collapses because there is no more current, okay. So you have a release of electric and magnetic fields that go out. And of course, this is a transverse electromagnetic wave, TEM, okay. So they are perpendicular to the direction of flow of the wave itself, okay. Similarly, next time the charge polarity is reversed in the voltage source. So you have currents going up that way, right, and then you have buildup of charges, okay, and then when the current polarity flips again, electric and magnetic fields are released, okay. So hence you have made some piece of wire connecting it to an RF voltage source, okay, something that's pushing out electric and magnetic field lines, okay. So this is an antenna as a transmitter. The exact same thing is applicable when you treat it as a receiver. Here you will have something that is receiving and it is sensitive to electric and magnetic field lines the same wave, okay. Things are coming in, it is exciting currents on the electric field lines, inducing currents, magnetic field lines, and that is something you can sense with the receiver. Okay, this is how a dipole antenna works. This is how any antenna works. It's just the shape and the details will change. Okay. Because there is a certain natural length of the wire and the frequency involved, okay, this dipole will be efficient at radiating or receiving at a specific frequency, okay, and that's the resonant frequency of the dipole, okay. So this for a certain frequency of radio wave that you are, say, let's say sending or receiving, okay, let us say that the corresponding wavelength is lambda of that frequency or that RF signal. it is resonant when the arms of the dipole are lambda by 4 each. Okay, hence the total length is lambda by 2 or a half wave dipole. Okay, I will not touch any more on details of antenna because there are many types of antenna, but the principle of operation is the same. It either transmits or receives electric and magnetic field lines like this. Okay, mostly electric, magnetic we don't really talk about, it's more in terms of the polarity of the signals. Okay. Okay. The next thing is you have done the sensing business. The electromagnetic wave has come and hit your antenna, and okay, I have to go faster. It has come and hit your antenna, and now it has excited a voltage at the terminals of this wire. You can think of this as a way to receive power. Okay, what you're sensing is power, because power is like the square of the voltage, right? V square by R. Okay. There's a concept of when you measure anything in radio astronomy, what you're measuring is actually, you call it noise. Okay, even if it is a signal, effectively it's noise. If you put a receiver there and you can say connect it to some way to connect it to make it audio, it'll go zzz, right? It's noise. It's like something like static. Okay. The way you characterize the noise is by using this concept of Johnson-Nyquist noise. In case you've not heard of it, it is just the thermal noise in a conductor or a carrier. Okay. So the standard way of writing this is that the power in that noisy system is equal to K, here's Boltzmann constant, T is temperature of that object, and B is the bandwidth or the entire frequency range. Okay. So what is this T here? It's not the physical temperature again. Yeah, it is not even brightness temperature, it is the temperature of an equivalent noisy resistor if you connect it to a receiver. Okay. So we have one temperature which is thermodynamic, one temperature which is the brightness, and the third is the noise temperature. Okay. The noise temperature can be of the antenna if you connect an antenna, it can be of the receiver because electronics are also noisy. Okay. So this is the equivalent temperature of a noisy resistor that would produce the same amount of power in a receiver. Okay. So we have P is equal to KTB. So we have collected the signal, we have converted it to some voltage, and we've expressed the voltage in terms of some units of temperature. Okay. Yes.
The Johnson noise is because of the equipments which we are using, or is it because of the signal itself?
It is due to the thermal motion of electrons. Okay. So it is not, so you can later equate the brightness temperature or the power you measure at your antenna to a equivalent noise temperature of a resistor. Okay. So that two different units, but you can equate the two and you can express the power you're receiving in terms of Johnson-Nyquist noise. Okay. But it is just because random motion of charge carriers, electrons, protons in a wire. Okay. It is noisy.
Because even the equipments which we use as like resistors.
Exactly. So all of that adds to noise. I think I have it in a slide here. Okay. Few slides away. I've not even come to interferometry, but let's see. Okay. Okay. Now, we talked about this, so I won't spend too much time. So this is a standard antenna, like a parabolic dish. It has a diameter d. Okay. Just from principles of wave nature of light, let us say, it can diffract. Okay. And the diffraction limit sets the resolution of a telescope, which means for a certain wavelength of light lambda and diameter of the dish d or size of the dish d, the resolution of the telescope or the finest object, the smallest thing that this dish can see has a size lambda by t. This is radian units. Okay. Lambda, both are in meters, dimensionless, so this is radians. Now, if you want the Hubble Space Telescope, this is the resolution, okay, in radians. Okay. And if you want the same type of resolution for at the lambda of say a millimeter, okay, you need a dish which has a diameter of 2 kilometer. Okay, the largest single dish diameter we have is that fast radio telescope, 500 meters. Okay, it's not steerable. Okay, so imagine a 2 kilometer large dish, impossible. Okay, so you can do this exercise, compute what should be d to get a similar resolution for at 1.4 gigahertz, which is a very standard radio frequency. Hydrogen 21 centimeter we spoke of. Okay, it will be enormous. Okay, you can't do this with one dish. You add many dishes and sorry.
You can take a certain points.
Yes, yeah. So that will come to So that we call it as aperture synthesis. You add many small dishes and it becomes like one big dish, okay. But quickly, there are many single dish radio telescopes. We spoke about FAST, I showed you green band, there are a bunch of these things. The idea is simple, like I said, an antenna is a device that can sense or receive electromagnetic waves. So very simple, I draw an antenna like this, okay. An antenna has a few properties, but the most relevant for today is something called as a beam pattern, which is basically the sensitivity of the antenna in different directions, okay. So this is an antenna, let's say, and let us say this is the beam pattern, which means it has maximum sensitivity to something coming from the top, zero sensitivity to something coming from the bottom, okay. And maybe it has, this is called the main lobe because clearly it's nice and big. It could have some funny things on the side, these are called side lobes, okay. So all of these are properties of the antenna pattern. So when I actually make a measurement of, so this pattern has a peak value, okay. I can take the beam pattern, this is basically a function of theta and phi, okay, and I can normalize it by this maximum value and I get something called as a normalized antenna beam, okay. Yeah. So the beam solid angle for this entire beam, technically it can be 4 pi, it can be in all directions, but practically you don't have an antenna that has 4 pi sensitivity. So you get the integral of the beam, normalized beam pattern gives you the beam solid angle, okay. And the total power that this antenna can measure is here, okay. So basically there is a effective area of this antenna, okay, which is not, if I have a dish or if I have some dipole or something, not all of it is going to be perfectly sensitive, okay. Practically there is an efficiency factor, okay. There is an effective collecting area of the antenna that multiplied by your brightness kT by lambda square, okay, and there is a delta nu because it is the total power you are measuring and the beam solid angle. So this is the total power that a single antenna will measure, okay. Now I can also write this in terms of antenna temperatures where I have taken out frequency explicitly, and this is the equation. So what I do is basically I integrate, multiply the antenna beam pattern and the temperature of the object I am trying to measure. That could be a galaxy, that could be some hydrogen in some direction, okay, and everywhere there is a theta and phi dependence, direction dependence. I integrate these and I normalize by the beam pattern, okay. That will tell me the antenna temperature that we talked about, okay. So this is the brightness of the object, okay, brightness temperature of the object I am receiving. This is what my antenna noise temperature will be. There is a relation. So how do I do this relationship, right? I am measuring something. Finally, at the end of the day, I connect my receiver to an antenna terminal, okay, and it is measuring some power, something noisy, okay. I want to convert that to some meaningful units. It is not telling me the power is or in so many watts or so many Kelvin. It is just giving me some bunch of voltages, okay. I have to meaningfully convert this to some temperature units, okay. This process of converting what you measure to some meaningful units is called calibration, okay, and calibration helps you do a few things. It helps you correct for some random, like not random, but some properties of the instrument itself, which I have called G here, some gain, okay. It multiplies, divides, it changes the shape, it does something to my measurement, okay. So the way I calibrate, there are many methods of doing this, but let's talk about a standard method. I take an object whose temperature or power I know, okay. For example, I can take an object that is at a physical temperature of 500 Kelvin, okay, and another object with some physical temperature of 77 Kelvin. I have dunked something liquid nitrogen and put it in front of my antenna and that covers the whole beam, okay. So I have what is called as a hot load and a cold load, okay. From the hot and cold load, I can cancel out the properties that are specific to the antenna beam pattern and receiver and get just some unit of conversion, okay, and that unit I can multiply with my observation, okay, and I can get my the temperature towards the object I am measuring, okay. I will quickly repeat that. I have an antenna that is looking at some object in the sky and I am measuring some units. I have no reference for that unit. I now replace the object in the sky with an object whose properties I understand, such as temperature, okay, and I can control it, okay. So I put a hot object, I measure some value, cold object, I measure some value, And from that, there are two equations and two unknowns. One is the gain of the receiver and some noise in the receiver. Yeah. Yes, so that's called linearity. So you want to try to keep the object you're sticking in front of your antenna or receiver kind of sort of in the same order of magnitude as the object I'm seeing. Because if I saturate the receiver, the gain is no longer linear. It will change. That means my calibration will fail. Okay, so we have to take care of these things. And then finally, you can convert that random number you measured at your receiver, looking at your source, okay, to meaningful units like temperature. Yeah. Exactly, yeah.
So we have a signal, so we set some primary signal which we know.
Yes.
And we set that phase log, like lower logging phase, upper logging
Yes.
phase, and between them we know.
Yes. That's exactly. So even in astronomy, radio astronomy, you have to calibrate for amplitude, for phase, okay, and you have to calibrate for some gain, which is the receiver. So there are multiple things you have to calibrate for. But this is the simplest calibration you can do, giving units to something whose units you don't know. Okay, calling something from XYZ, some random noise, to temperature. Okay. 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 All right. So we talked about signal. We talked about noise. Okay. So there is an equation that tells you what is the signal to noise ratio, which is how good your measurement can be with a receiver. Okay. So the signal to noise ratio is, or actually this is the noise, not the signal to noise ratio. The noise in a receiver given by sigma t is the ratio of what we call system noise to the square root of bandwidth and time. I'll spend some time on this slide and maybe we'll not even touch interferometry. Let's see. Okay. Okay. So the noise in the receiver is better expressed like this. Okay. You have a square root 2 everywhere and that cancels out. The simple argument is the following. First of all, what is this thesis? Okay. Like we talked about, you have a antenna looking at an object which is a source. Okay. Here this is this source term, delta source. Okay. The antenna will see other things also. It's not going to see only the source you care about. It will see other sources in the sky. It will, for example, also see this cosmic microwave background we talked about. Okay. It will see things like reflection from the ground, because we talked about back lobe and side lobes that will look not just upward, but you can also look sideways, and there could be a hill there, some other tree there, it will look at everything. Okay. So that is called spillover. Okay. In addition to that, it may have it may see the atmosphere, because atmosphere, even if it is not at very high frequency, it adds some noise. Okay, and there is some optical depth to this. We already discussed this. And someone asked, what about noise in the receiver? There is noise in the receiver. Okay, and the idea, the name of the game is we have to try to minimize the noise in the receiver so that it doesn't dominate all our measurements. Okay, there are techniques to do that. So finally, your system noise is the combination of everything. CMB, other objects in the sky, the source you care about, atmosphere, things that the antenna will see that you don't want it to see, and receiver noise. This goes in the numerator, and we didn't spend, okay, so the noise temperature that I discussed, right, the thing that you have a Johnson-Nyquist noise. It is a Gaussian in nature, it's random noise, okay, which means it has a Gaussian profile. Okay, in radio astronomy, for the most part, you operate in the limit that the noise your receiver sees is Gaussian in nature. Okay, that means it has a flat spectrum. Okay, and it's there in the references. Again, I'll point you to them. When you take the sigma of the power, not the voltage, you get the square root term. Okay, there's a square root and this thesis. In the denominator, effectively, is just the number of samples. Okay. If I am collecting data from a receiver, from a telescope, there is something called as Shannon-Nyquist sampling theorem, which tells you have to sample the signal at least 2 times the bandwidth or the highest frequency. Okay, so you have a square root 2b. Okay, and you take multiply by t. So square root 2bt is the total number of samples n I get. Okay, so the root 2 cancel. And I have the noise in my receiver is the ratio of the system noise or system temperature square root b tau. So I can increase t, okay, the time I observe, or I can increase the bandwidth of my observation, or I can reduce all of these terms to reduce the noise. So signal to noise ratio is nothing but delta T source by this sigma T. You want to maximize T source by by sigma T. Okay? Yeah. Oh, this is so the atmosphere is an object which this is radiative transfer equation. Okay, so you can think of this is the source function. Atmosphere itself is emitting something, but it doesn't come to you directly. It has to come through itself. It has to come through the atmosphere, and the atmosphere has an optical depth. Okay, so that is this term. For very low frequencies, the atmosphere is optically thin. Okay, so it just you have some small term, and that term is usually very small. So this term goes away. Okay, and you just have TATM, and TATM itself is very small at low frequencies. This starts becoming significant at the 100 gigahertz, 10 gigahertz. That's why we go to higher altitudes. So that then the 1 minus E tau TATM is also small. Okay, for higher frequencies where it is significant.
So the T system represents the noise of the system?
Yes. Yeah.
So it should be noise to signal ratio?
No, so this is not the signal to noise ratio, this is just the noise term. Okay. Sigma T is the noise in the receiver. T system is in, I think I started out by saying that in radio astronomy noise and power are the same, they're interchangeable, everything is noise, even what you're measuring is noise. You have to get your signal out from the noise that you measure. Okay, this is the total receiver system noise, which includes receiver noise and everything you measure. So the final signal to noise ratio is equal to your T source that you're trying to measure. I think in my equation there I've called it delta T source, because when you put a receiver on the sky, when you point it towards your delta T, your source that you care about, the temperature goes up by a bit because there is a source there. Hence, there's a small bump, that's the delta T, divided by the sigma, okay, which is nothing but delta T source by T sys into beta, okay, tau or T or whatever. Okay, this is the signal to noise ratio. So you want to increase your signal to noise ratio, you can either increase B, increase T, reduce T sys. This you don't have any control over, this is coming to you from the sky, okay, but you can decrease this or increase this. Okay, I have 7 minutes, I will try, okay. This is where we start getting into interferometry. Okay, so far I'll just quickly recap. We talked about things you can study at radio frequencies. We've talked about how a basic telescope works. You have an antenna, signal comes in, it becomes a voltage. The voltage goes to some receiver that may have that concept of heterodyning, and that goes to some digital part which I will not cover today, someone else will talk to you about it. Okay. We've also talked about the concept of power, different temperature units, thermodynamic temperature, brightness temperature, antenna or noise temperature, and the concept of signal to noise ratio, and how the antenna beam pattern is sensitive at different directions. We also talked about the resolution of a telescope. Bigger it is, smaller your objects you can see. And we have seen how a single element or a single dish dipole type of a telescope can work. Now you want to increase the number of telescopes, okay, and try to detect some object in the sky. How does that work? Okay. So the starting point for that to understand is that, let's say you have some object in the sky, okay, I will point here. So there is some object here in the sky, okay, and it is doing the same thing. There is some electric field coming out of it. It's at a location R. It's a time dependent function, but for today, for now, this is simplifying assumption, we forget time. Okay, it's there, it's coming to us, we observe for a finite time. Okay, so this electric field at a certain frequency is coming from a position R. We are here, okay, this is us. We are measuring some other field, okay, because clearly we won't measure everything that it's sending, and we are at this position small r. Okay, this comes to us through a medium. Okay, assume free space. Okay, assume for this today space is empty. You are not in the optically thick limit of the ISM. Okay, it's coming to us with some propagation factor, which just decides how this wave comes from that point to this point. Okay, Yes, most of you, I hope you know what is this Huygens principle. Everything is plane parallel waves, it just comes to us, but there is a delay, okay, there is a phase, okay, and that phase is a function of the distance, okay, and that's what I've written here, okay. But what you do here, okay, I've jumped over a few steps. This electric field that comes from here, I'll make one simplifying assumption that it comes to us from infinity. So even though it may not be from infinity, for your purposes, it's a plane parallel wave coming to you from infinity, from some celestial sphere, okay. So there I rewrite this capital E as this some epsilon, okay, because I projected this object which has some shape and size onto this sphere. So this projection is this epsilon, okay. So this epsilon at this r comes to us after some propagation, which is basically a phase delay, okay, and it comes to us at our source small r, okay. This is what I am measuring. Now assume that I am trying to sense this field at 2 points, okay, r1 and r2, okay, and I take a correlation, okay. Correlation is nothing but this: I measure at r1, I measure at r2, they are all complex vectors, so I take a complex conjugate and I average. This is a correlation, okay. So when I take this correlation and I rewrite in terms of this equation, okay, this is what I get. This is my correlation function.
Is that potential?
Sorry?
Is that electric potential?
Field. This is field, okay, electric fields, okay. So this is what we are getting. So we basically write this equation in this equation 2 and 3, we get this, okay. You would have noticed that there are some terms missing, okay. The terms that are missing are the cross correlation of epsilon capital R1 and epsilon conjugate capital R2, okay. They are cancelled out. That is because for most objects, okay, astrophysical objects are not correlated across the sky, okay. You have, so only things coming from one object are correlated, things that are coming from different objects are uncorrelated. So the capital E terms in the correlation disappear. So finally in my final correlation, and this product is called spatial coherence, okay, you are getting all the information of this object at capital R after some phase delays, okay, and you are getting this at capital R, small r1 and small r2, okay. I will maybe work this out on the board outside. I am trying to rush for time and not working it out on the board, but basically what you get, this term, okay, that you measure here is called the spatial coherence, okay. The term that I have written here is a simplification of this, where this field square, okay, is giving me an intensity, and my r square ds integral over the area is giving me d omega, okay. And I have rewritten this r by small r as a unit vector s, okay. That is what this small s is, okay. So finally what I have is the correlation between 2 points of the field that I receive from an astrophysical object is related to its intensity, okay, by this equation, okay. Yes, okay. So basically what this is telling you is, I can have two telescopes a distance apart looking at the same object in the sky, and I will be able to measure its intensity as a function of this distance, okay. Yeah.
These telescopes have to be followed same baseline.
So I'll come to what baseline is quickly. So now how do I implement this in practice, okay. I can put a bunch of telescopes across, scatter them across some area, and the separation, this R1 minus R2, right, this R1 minus R2, if I divide it by lambda, the frequency at which I am observing, that is called a baseline, okay. It is a vector quantity because R1 and R2 are vectors. R1 vector minus R2 vector divided by lambda is called baseline, okay. So I can put a bunch of objects like this. Each of this dot here is the position of a radio telescope, okay. I can call this plane on which I have the objects the UV plane, okay. There is also a W term which is like x, y, z, okay. The z is the W term, but assume it is a flat surface, okay. So I ignore the W term. on the UV, if this is the UV plane and this is the plane of the sky, because remember we have projected everything into some infinite sphere, so it's a plane now, it's a flat area, and that is the LM plane, okay. I can write the same correlation, okay, with setting the, this W term to 0, and I can write it in terms of, here I just had it in terms of some vectorial representation, okay, I had it in terms of some vectorial representation here, but I can write this again in terms of x and y coordinates, or in our case L and M coordinates. I get this equation, okay. This is called the Van Sittard-Zernike theorem, okay. Don't bother trying to remember the name, but it's a standard jargon you might hear people say. It tells you that this is the relationship between the intensity of the object in the sky and what you're measuring here on Earth when you have an interferometer, when you have two telescopes trying to make the same measurement, okay. Yeah.
All of these we are doing at a fixed time. So
At a fixed time, yes, yes.
But when we count the time, then it will be an extended equation.
It will not be an extended equation in the sense, okay, practically what you do is you take instants of time. You record voltages at instants of time, and then later you average it. And your averaging helps you with your signal to noise ratio, okay. If you make your instant of time very, very large, I'll jump over this slide, it's not very useful right now. Okay, this is what you'll see. You saw that UV plane, okay, UV plane had these dot, 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 each of this is like a baseline, okay. You let the Earth turn, the projection of the baseline on the sky or vice versa changes. You can fill this UV plane using tracks like this, okay. So the more this is filled, the more information, the more samples you have on the object at different baselines, okay. And that is how you make your, okay, so let's recap this relationship. If you pay close attention, you will see that the source you have and the visibility have a Fourier transform relationship with the measurement, okay. So the spatial correlation function that you measure has a Fourier transform relation with the intensity of the object on the sky. That's what we arrived at. We will work it out on the board later. I had to jump over it. But this is the relationship. And you can make a measurement of these visibility. This is the visibility plane, okay. This is what you get, okay. So you have, this is the object, this is the beam that you have, okay. The visibility of your object looks like this, the Fourier transform, okay. The UV plane coverage, okay, how many samples you have on this object is like this, okay, that basically determines how noisy your beam is. And finally, you are able to get a sample of this UV plane, number of samples on that object you are trying to measure, okay. So you can make an image of the object. So this is what you make. You end up making this map, which clearly looks dirty. So your calibration processes and offline processing will correct for this dirtiness and try to reconstruct this. So you have two sources here, you have a noisy beam here, you get a noisy map. In practice, what you're doing is everything is in the sampling domain, in the Fourier domain. So okay, you make the Fourier measurement, then you do the inverse Fourier transform, you get the dirty map, you cancel out the properties of the beam, you reconstruct the image, okay. So yeah.
It looks like an airy disk pattern.
It is, because remember finally it is a diffraction pattern of the interferometer. Before you had diffraction pattern of one dish. So now in an interferometer, the baseline gives you the lambda, the dimension for the diffraction pattern. So this is like the diffraction pattern of the not one antenna but a pair of antennas. So you have many pairs, you have interesting patterns, and that's you have to deconvolve in the processing.
Baseline is R1 minus R2 by D.
By lambda, yes,
By lambda.
yes,
And sensitivity is like D by lambda.
yes.
So by how this is connected to the resolution of the total.
So here in your equation you had lambda by d, that is the resolution, not sensitivity. Lambda by d is a resolution. So here this is the d, okay. For an object coming from a certain direction, there is a projected baseline. So lambda of the object divided by this d is the resolution. Further your spacing is related to the wavelength, the finer your resolution is, okay. So I will stop here because I've gone way over time, at least 5 minutes over time, and we can continue outside. So this is finally, I'll just stop here So you take an image like this, its FFT will look like this, okay. This is the 2D FFT. So in UV plane, this is the amplitude of this person and this is the phase. So what you will measure with your instrument in voltage, okay, is actually this. If I take an inverse Fourier transform and I can reconstruct this image. But in practice, of course, you don't measure people, you measure galaxies and so on, okay. And I'll leave with this slide. So with this concept, basically using the properties of spatial coherence, spacing of the antennas relating to its wavelength, you can make very detailed objects, images of beautiful objects in the sky. So this is Cygnus A, okay. So you can see this is, I don't know if it's visible to you from there, but this is the large scale structure, you know, there are jets and hotspots and doing whatnot. You can zoom in on this at a higher frequency, okay. You can get higher resolution, okay. Then you come to this, you can zoom in on this, come to this, zoom in on this. So you can get like a, you know, high-res camera, you take a picture and you can keep zooming in and see more details. You can do that at arc-second resolution, okay, like better than Hubble, because your limit is only the number of antennas and telescopes you put and how far away, okay. The larger they are, the more detailed. So when you put them at very, very large distances, for example, other ends of Earth space, okay, this is called large baseline interferometry, VLBI, very large baseline, and this is a VLBI image from the VLA array in US.
What are those 3 millimeters, 7 millimeters?
Oh, this is the wavelength or the frequency of the measurement, yeah. So each of this was done with a 6 centimeter, which is like, you know, some 10 gigahertz or something.
So then if ideally if we able to cover the equator of the Earth,
Yes.
we can measure like what is the frequency range we can use for?
Well, frequency range limit is set by ionospheric stuff, so that sets your limit. Across Earth, you do VLBI offline, you don't do it simultaneously because you can't look at the same direction of the sky from different parts of the Earth. I think we've gone to, if I'm not mistaken, I think we've gone to micro arc second is the highest, the EHT kind of stuff, okay. I could be wrong, but we've gone really, really fine in across wavelengths in radio frequency.
And one more, like how do we come on relativistic errors like micro gravity, micro?
I don't have a good answer for you, okay. I mean, there are a lot of correction terms, you have to do it, put in, and we have not talked about calibrating an interferometer, we only spoke about standard calibration. So first of all, you do standard calibration terms. I don't quite know, are you talking about in terms of VLBI, these corrections? Okay. I think VLBI biggest problem more than anything relativistic is just ionospheric and atmospheric, because you have one patch of cloud over Bangalore, you have something else or clear. So there are these phase problems that are problematic in VLBI. I'm not quite sure about relativistics. Okay, I will stop here. I know the last part we kind of jumped through, but hopefully you've got a flavor for how we make measurements in radio astronomy with one antenna, and if that's your takeaway, you're way ahead. So this part of interferometry is the details of how you make multiple antennas behave like one large antenna to get the better sensitivity, resolution and details, okay. So I'll stop here and we can chat.